So I will be talking about some formal language theory. And the work up to now is mostly about coming up with a proof, because the original proof there were some issues that we will see. Let's start. So I have a list of topics. I don't know how much I will need to skip, but basically, yeah, we see about the context of the problem. So multiple context-free grammars and balanced strings, which gives the general idea about what it is all about. And we will see a bit about some idea about the pre-existing proof, which interestingly is geometric. And then we introduce the new proof, which is combinatorial, so it tries to cut away on the geometric bits. And I have some work in progress in Isabel, trying to implement this proof. And also some computational experiments that I got from the Isabel executable definitions. So I hope there's something interesting there. Okay. Let's start by something hopefully known to everyone. So the usual context-free grammar. So when you have a context-free grammar, as you probably know, like here on the right, you have some rules, and uppercase stuff is called non-terminals, which are basically placeholders that you can replace in whichever way you want. And by doing this, you obtain a parse tree, which terminates when each non-terminal is replaced by a terminal, which is standardly denoted by lowercase letters. So from the grammar on the right, which I shortened, I omitted some rules, of course, but basically you can produce sentences like here.
Can I say that's a very British-German sentence and very troubling in a scientific talk. But
well, I only found more trivial ones. I changed randomly. So basically, yeah, I used the parse tree and replaced the non-terminals, basically. With something that made sense, but maybe I was not in a good mood.
Yeah, maybe it has some Freudian flavor to it as well.
But all of linguistics has a very Freudian. All the examples are not quite safe for work, I would say, in linguistics.
Well, I hope that is not too troubling for anyone, but yeah, I will change it maybe. Okay, this is just a quick refresher, so hopefully not too complicated. However, from this simple concept, you can have a more logical, logician point of view. So the same rules can be regarded in a bit more logical way by just thinking of the non-terminals, the capital stuff here, as unary predicates, taking as arguments strings of terminals, and they will basically, each of them will return true or false according to whether the terminal string you pass as an argument can be generated by that non-terminal. And in this case, we just reverse the reverse of the arrow to denote the fact that basically, we have a conjunction here, so we placed a comma between the non-terminals, which are now returning booleans, so it's basically a conjunction. And then we take the conjunction of the values returned by the predicates, and there is an implication now, that's why we reverse the arrow, which say, well, if this returns true and this returns true, then it's also true that this other function returns true on the composition, right? Okay, again, hopefully nothing too complicated. And basically, this is the general idea now. Whichever rule you have, you can rewrite it in this way. So you have E0 taking some terminal string, and the same. You take the conjunction and take an implication and check whether you're allowed to return true for the other predicate. Depending, and the base of the rule is how you combine these placeholders in the argument of the left-hand side, okay? So, a very mild generalization of this is to allow the unary predicates that we just saw to take more than one argument. So this creates something a bit more powerful than normal context-free languages. So you have something like this. The same as the last line of the previous slide. The main difference is that now each predicate takes more than one argument. That's it. So, as before, the x's on the right-hand side are placeholders, meaning that they stand for terminal strings. And on the left-hand side, basically the nature of the language is given by how the y's combine the placeholder x's on the right-hand side. Okay, so this gives you more power because basically what you have now is the possibility of combining bits of sentences in more than one way, more ways than you are allowed by context-free grammars alone. Okay, and that's the main idea behind this kind of grammars. You can have different flavors of this idea. The one we will be looking at is called multiple context-free grammars, which is basically this approach with some additional constraints here. So, first of all, we impose a linearity on the axis, meaning that you have several variables which are pairwise distinct, second constraint, and the other constraint is that each of them will appear exactly once in the left-hand side of the rule. So, I skipped the definition because it's really tiresome and tedious, but the main idea is hopefully clear enough. And we just skipped one example. So this is a possible multiple context-free grammar. And on the left-hand side, you have the trivial rules. Let's say they look like actions, basically. From nothing, you can get this kind of non-terminals. And each non-terminal on the left-hand side takes two terminals, which are letters. In this simple case, the alphabet is only 4 letters. They are paired 2 by 2, so A and conjugate A, B and conjugate B. On the right-hand side, you have let's say the more interesting rules, especially the first 4. So they tell you how you can combine bits of your sentences once you have generated them. So you only have basically one binary predicate here, 2 arguments, and it tells you, well, if you have originated maybe starting from here, you have originated some combination of A and B's, then you can get other combination in this way, by concatenating them and in this type of way. S is just the usual starting symbol. It doesn't have a big role here. It's basically your final step, right? Well, once you have finished, you obtain some pairs of strings that you like, you can just concatenate them and finish. So the interesting predicate is basically on the I here. Okay, the first thing one might notice is that since you always introduce letters in pairs, the A and conjugate A and B and conjugate B and so on, always together, whatever strings you generate using this multiple context-free grammar is balanced, which means it has the same number of A conjugate A's and the same number of B and conjugate B. And we call this type of language O2, where 2 stands for the fact that we only have A and B. But in general, you can have ON. So you can have N letters and their conjugates, and you just require that the number of letters and conjugate is always the same number of occurrences, okay? When you're working in O2, it's customary, instead of write A0 and A1, you just write A and B, just for convenience. That's what we will do. Okay, now the interesting question is whether the converse is true. We saw that it's easy to understand that you can only generate balance strings, but is it the converse true? Whichever balance string that you have, can it be generated by this grammar? So, this grammar is just an example of MCFL, but if we manage to show that this particular grammar can generate O2, then we get an answer for the general question whether O2 is an MCFL, of course. And that's what we will try to do. And this question, I will skip a bit on how this question originated, but basically there are a number of extensions of context-free grammars conceived by both linguist theorists and algebraists. Interestingly, because there is a nice relationship between this type of grammars and the word problem in computational group theory. I will skip a bit on this, also because I'm not sure I get it right. Anyway, this problem arose from that context. In particular, this problem arose from a more difficult problem relating O2 to a more restricted set of grammars, which has somehow important implication in group theory as well. But the original question is too difficult. It's been open for 30, maybe 40 years now. So in 2015, okay, sorry. In 2015, Salvati managed to show this weaker conjecture, which can also be looked at as a stepping stone to a more difficult one. So basically, it took this slightly bigger family of languages, MCFLs, and showed that O2 is indeed in this family. This proof, as mentioned, was geometric, and which was then revised and a bit simplified by Nederhoff the following year. Up to then, the proof was only applying to the case 2, so O2, only 2 letters. And then, after some years, Hall managed to generalize the proof to ON, but with bigger fan-out than needed. So the fan-out is just the term for the arity of the predicate, right? So fan-out is the number of arguments that each predicate can take. So Hall generalized the case to ON, but with a non-optimal fan-out of predicates. And then, after some years, a fully satisfying proof was found for ON, about being an MCFL, with optimal fan-out. This means that the number of letters, if you have n letters, then you only need predicates taking n arguments to generate that language. Okay, this is an example of a parse tree for the given G2 that we saw before. I reproduced the rule here just for your convenience. And basically, we see how this balance string can be generated using the different rules. Okay. And so the question, of course, is, whenever we have any balance string, can we generate such a tree, a parse tree? Well, the first thing I did in my own proof was to basically forget about the grammar and only think about tuples of factors of a balance string. So, right? I basically don't care much about the particular rules. I just look at the general problem of, as follows: I'm given a balance string which is split into arbitrary factors. And the idea here is that in whichever balance string you're given, and in whichever way it's split into 2 factors, you can always split it further into 4 smaller factors, such as they are related in pairs, they are balanced. So these 2 pairs form a balance string, and these 2 pairs form another balance string, and both strings are smaller. This is the key point, because if you get smaller strings, then you, of course, can improve things by recursion or induction, right? So the key point now is really to find a general way of whichever pair I'm given, which is balanced, I need to find a way of splitting it. So, and I will call this way, this a balanced decomposition. So I'm given two factors which are together balanced, and I need to find four factors, two by two balanced. So, in this way. And then I will call this a balanced decomposition of the original pair. So, some examples. So here I have two way of splitting which are not balanced decompositions. Okay, the problem with the first one, this is not balanced, not a balanced decomposition, not because of problems in the balance, so you have factors which are balanced, but the blue are two factors, but the black ones are together balanced, but they are three. So this is too much cuts. In the second case, we have two pairs of strings, two blue and two black, but they are not balanced. So these are not valid decomposition. On the other hand, we have a number of valid decompositions, of course, and I didn't list all of them. So that we have the same pair of balanced strings, and there is a number of possible ways of getting decompositions. So as before, the two blue strings are balanced together, and the two black strings are balanced together. Yes?
So what you mean balanced decomposition means that this can be parsed? Yes, or
Can be what, sorry?
can be parsed. I mean, what is your definition of balanced decomposition? I missed it. So.
I written the definition here, I have it in the paper, but basically it means that you have whichever pair of factors of a balanced string,
Yes.
you can cut it with at most two cuts. So here you have one cut here between the blue and the green, or yellow, sorry, I'm colorblind, and another cut here between the blue and the green, right? So you have two cuts, and in this way you got two pairs which are...
So you want a single way to cut, yes? That's what you're saying.
No, I mean, in general, there is more than one way to cut, but I can only have at most two cuts.
So a balanced decomposition means you have at most two cuts.
Yeah.
Okay, that's fine. So it has nothing to do with parsing for the moment.
No,
It's
no. As I said, for the moment, I forget about that.
Okay, sorry.
It's just a problem of strings now. Yeah.
And it also nothing to do with the numbers of bees.
Well, they just need to be the same. B and conjugate B needs to have the same occurrence. That's the definition.
In opposite elements of the pair.
No, globally.
Globally, yes. So here you have two B's in total and two conjugate B's in total, but they don't need to be in the same factor.
Yes.
They could be spread. Yeah, so for example, here we have in the black part we have two conjugate B here and two conjugate B. Sorry, two non-conjugate B, and you have two of them and two of them. So the part in B is balanced, and the same holds for A. And here, if you take the black parts in this second line, you see that it doesn't matter how they are mixed. The only thing we care about is that all the black parts in total has the same balanced occurrence. Okay? So same number of B and conjugate B, same number of A's and conjugate A's. Of course, the number of B and A's doesn't need to be the same. Maybe it will get clearer with the geometric view that we introduced now. Okay, so this is just a statement of the problem. The original proof had a geometric interpretation, as I said, and the geometric interpretation is quite natural. So you have this key. So you move one step on the right when you see an A, you move one step up when you see a B, one step left when you see a conjugate A, one step down when you see a conjugate B. In this way, for any pair of strings, you can construct a walk. Here, the circle is the origin, so you start from here, and you move A, so 3 steps. Then you see a B, you move up, and so on. When you finish the first factor, when you're right here, this is denoted by a solid circle, point P. I just gave a name to that particular step, because it's an important part of the curve. And then you go on with the second factor. So you see a conjugate A, you move one step left, and conjugate B, you move down, conjugate A, left, and so on. Okay, the first key point is that since the 2 factors, when put together, form a balanced string, it always means that the curve that you build this way is always closed. That's the key point.
That's in 2 dimensions, no?
This is 2 dimension in O2.
You have A and B. When you have 3, you have 3 dimensions, A, B, C.
Yeah, and the 3 dimension.
Notice you can also do that with primes. You design a prime for each letter, and then the prime for the conjugate, and then it's an equation. When the equation is 0, it works.
What do you mean equation? You mean tuples of?
You have a number of A's, k number of A's, that is K for a prime, k number of conjugates of A, that is K times this. Negation of the prime, this is 0, and if
so you're mapping,
you're
mapping the problem to Zn, basically to tuple.
I think that this can be also represented by multiplication of primes and negation of primes, and you will have the equation equal to 0.
Multiplication or summation?
Well, if you have 3 occurrences of A, it's 3 versus 11, right? You add 11 3 times.
Yes.
And you subtract 11 3 times.
Yeah.
And if you choose primes, the addition of this equation will be 0 when you close this gap in 2 or 3 or 4 or 8.
Yeah. Yeah. Basically, this is basically actually you don't need the real plane. You can use integer numbers, of course.
Mm-hmm.
But the interesting fact is that passing to geometry, meaning that real plane, gives you some tools that you don't have if you look at in the discrete way, and we will see why. Okay, so you get a closed walk, and it's it's useful to have this geometric representation because some notions become immediate. So one first notion that we point out is the shortness, so-called. So in this example, you see you go from O to P using one string, and from P to O back using the second string, right? If you take each of these 2 strings separately, each of them is short. It means that whichever walk you take from O to P can have a minimal length, and when you take a short string, it just means that this path cannot be made shorter than that. So in this case, you have 1, 2, 3, 4, 5, 6, 7 steps to go from O to P, and you cannot find a walk with fewer steps. This means that that particular walk is short, and that's the definition. And we will say the same about the corresponding string. So this geometric interpretation allows us to give a definition of shortness for a given string. For this bit, you don't need geometry. Of course, you can give a definition in terms of discrete stuff. However, this other property is more interesting and quite inherently geometrical. So I took another string, as before. I start from the origin, I move some steps until I get to this solid point, and this will be my first string. And then I go back from this point. Oh, sorry, the arrows are wrong here. No, what did I do? No, the arrows are right. I follow the wrong So we go back to the origin from here following this path, okay? So the important property of this curve, it's that it is not simple. It means it intersects itself, exactly in this point. And it's quite an important property because basically, if you take a walk starting from here, you have another closed curve. It means that you can find decomposition because you have two balanced substrings. So in this case, for example, I highlighted in colors. So I can use this particular rule to see that I have decomposition. And I know that just by looking at that. I know there is a closed loop here. So I know if the curve is not simple or self-intersecting, then the case is easy. So that's something that helps Salvati in the original proof. And just to see the benefits of the geometric interpretation, now we have a very simple result if you think in geometric terms. So if you start from a short and simple pair of strings, then they must have this form. It means that the first walk starts in one way and the second walk starts in the opposite way. How to see that? Well, by exclusion. So you keep in mind you have a short and simple pair, which means short means that you start from the origin and you get to this point along the shortest path. This means that when you start from here and get here, you cannot come from this direction, right? Because it's too long. Same here, you cannot come from up because you start from down. If you come from up, it means you took to walk along a walk, right? So the only options remaining are this coming from below or this coming from the left. But coming from the left is also excluded by virtue of now really geometrical arguments. Why? Because if you come from the left and then you want to go back here, whichever path you have taken in the middle, you must intersect it. And this is really obvious to see once you picture down. So you have to take the first walk to here, you need to go back to the origin because it's a closed curve. And I don't care about the intermediate steps. I just know that to go back from here to here, I need to intersect it. Or if I don't want to intersect it, I need to take a non-short walk. So this was one key argument in the geometrical proof. Okay, of course it's much more complicated. This is just a particular case, short and simple. So you have two strong assumptions. And if this short and simple assumptions falls, then things get really complicated in the original paper because you have a lot of geometric arguments you need to take. One of them is one of the simplest ones is something like this. So I just try to give an intuition. So as before, we go from the origin to the point P. And in some cases, some walks are really non-short. So you take a big detour. And now imagine to take a segment parallel to the line from O to B, from O to P, sorry. And imagine you start moving it, keeping the parallel condition. So at some point, the intersection between your curve and the line that you move will have the same length as the segment from O to B to P in some configurations. And you know that these two intersections basically can fall on integer points because the slope of these two lines are the same. So you can find an intersection where the length of this segment is the same as the length of this segment, and the intersecting points are integers. And this means that you have found a good decomposition. Why? Because then if this holds, then the two bits going from the origin to this intersection point, and from this intersection point to P, are balanced. Again, this only cannot be applied in some cases. So the problem is that you have a lot of possible cases in the original geometric proof. I just took an excerpt here. The proof goes for around 30 pages, if I remember correctly. I mean, the paper is around 30 pages, and there are a massive number of algebraic geometric tools and cases. Nederhoff simplified this thing a bit, but still the proof is relying heavily on geometric intuition or geometric abilities of the human. So now the problem is that how to make this argument understood by a computer, I don't know. And I might be wrong, but I see some reminiscence with the talk by Alexei last time.
Yes.
Contrary to his approach, my approach was basically to cut away geometry entirely.
The graphics, well, these are only for two symbols.
Yeah, this is still the case O2.
Okay.
So this is an algebraic geometry proof,
Uh-huh.
and it's quite complicated. So, yeah, basically at some point I started looking at the problem. To be really honest with you, my ambition was to try to beat them, but I couldn't. They came out with the generalization. But still, I mean, this paper basically settles down the problem in a very nice way. You have a very general proof, and it's still geometric, but the nice thing is that they also give you a combinatorial result, which, however, is not so simple as well, again, and requires some machinery. So, nevertheless, I thought that my proof could be interesting because, although it's less general than the final one, it's arguably quite smaller, and it requires only elementary notions. No Ivan lemma or Tucker's lemma. It's really just about counting stuff and taking some cases, not too many cases. We will see. And another interesting point of my proof is that it's somehow constructive, meaning that we will see it reduces step by step to the short case by removing pairs of letters at a time, which gives you possible basis from a recursive implementation of a parser. More on that later. Okay, just to give an idea, this lemma is from the new proof, so I wrote it, and it's just, I reproduce it just to show the kind of reasoning I have, so there is no geometry really. If you remember the previous, in the previous slide we saw the short and simple case here, and in the previous slide here we were talking about how to geometrically solve the simple and short case. And this is basically an equivalent result without geometry. And notice that it doesn't even require self-intersection, which is inherently a geometric property. So it removes some assumptions and has a fairly elementary proof. Of course, now we have the short case, which we will use as a base case. So we have the short assumption here, which is key to the easy proof. And now, basically, we need to reduce to this case. So how to do that? For the non-short case, we introduce the notion of a bump, which has a very simple definition. So a bump is just a minimal non-short string. So something like this in 2 dimensions. That's why the name, it looks like a bump. Minimal means that whichever proper factor you take of this string, it's not, it's short, okay? But the whole string itself is not short. Of course, you can go from this point to this point by removing the vertical bits, and you will obtain a shorter Okay, so for any string in O2 or ON, actually, we have definition. B of P contains all the bumps, and they are encoded by their start and end as a factors of P. So B is basically a set of pairs of integers, of natural numbers, sorry. And similarly, we can restrict this definition by only putting in the set bumps having some particular directions. This is just a definition which will be useful in what follows. Okay, why is this important or interesting? Well, because it's useful to reduce from the non-short case to the short case for which we have a proof.
Sorry, but it's when you call the start and the end, when you call
This
the occurrence.
Sorry?
So you say the start and end of all the factors.
Yeah.
So when you call the start, the occurrence in the word.
Yeah. So if you
It's the number. It's just a number.
it's just a position where a bump starts and ends.
Yeah, but position in the word.
Yeah. Inside P.
It has nothing to do with the drawings. It's just the position.
Yeah. It's totally non-geometrical. I mean.
Okay.
Yeah.
Fine.
Yeah. Sorry. The start and end. Yeah. It's not very clear.
The occurrence in
Occurrence. The occurrence as a natural number.
Okay. So you're trying in a way to build a notion of maybe bracketing, or I mean, you have a start and the end for all these parts.
Yeah. They're just occurrences pairs.
But you remember what is the start, what is the end, or you just take all the starts and all the ends?
I put them in pairs. Sorry. Yeah. It's not. I didn't want to go into
It's like a
the.
bracketing.
Yeah. So
Kind
you.
of bracketing, which is not well bracketed, but it's well bracketed.
Well, yeah, you can think of conjugates as brackets if you want, yeah, because we have opening and close, but they can also be switched, so it's not like brackets, really. No problem, thank you. Okay, now the obvious but important fact is that whichever string P, not necessarily balanced, that you take, let's say in two letters, A, B, and conjugate, it's short if and only if there are no bumps in P. So the idea now is to reduce to the short case by removing bumps one at a time, and we do that in a suitable way. So the important thing is that we always remove a bump of minimal length. So in general, B of P will contain several bumps if P is not short, at least one. And then what we do is look. Oh, yeah.
Why will you do the middle one? Start with the middle one.
Should be clear in the next slide. So it's very important that you pick a minimal one, but because otherwise the proof doesn't work. I mean, to be short. I hope to explain that in the next slide. What we do is we try basically to have a inductive proof or recursion if you're trying to build a parser. By removing always a bump of minimal length. By doing this repeatedly, of course, at some point we would reach short strings for which we have a proof. So if you take the induction assumption, of course, once we remove any bump, in particular a minimal one, we obtain a balanced pair which is decomposable. This could be decomposable in several ways. Remember, you only need to have at most two cuts. So you have a lot of possible ways in which by removing a bump you have a decomposable pair. I take one possible configuration here. So you have the two strings. These two strings are separated as usual by a comma, so they are a couple of two strings. And when you concatenate them, you obtain a balanced string. And I also removed one bump here. So bump, remember, in the two dimension just means you have a letter, in this case A, then another letter repeated, and then the conjugate of the first letter. This is a bump by definition. So I remove the bump, so it means I still obtain a balanced pair. So the concatenation of the string with but bump remove is still balanced. And here, P0, P1, P2, and P3 are just strings I don't know. I know nothing about. I just know that they are globally balanced. And I also focusing on alpha and beta, so there are two letters which I don't know anything about up to now, but I will try to reason about them. And finally, if you remember in a previous slide, I had an example where I had this notation. This just means that the factors under the braces, when you put them together, are balanced. So this is a decomposition. A and B together will give you two strings which are balanced, and same for the non-underlined bits. So this means A concatenated, the B part is balanced, and same for the other two. Yes?
So do you pick the shortest bump to deal with nested bumps? Is that
No, the notion of bump itself is never, well, no, you're right, it can be nested, but that's not the main reason for which I picked it. By the end of this slide, I hope it should be clear. Okay, one first obvious reasoning that we can have is that, well, this decomposition must straddle the cancelled bump. Why? Because, for example, if this end of B would fall inside the bump, I could easily reinstate the cancelled letters and I would still have a balanced decomposition, right? If both the cancelled letters fall within one balanced pair of factors, then there is no problem reinstating it. The two factors would be still balanced. So I must assume that the non-trivial case, the ends of these two braces must fall one inside and one outside the bump. Another thing I can assume easily is that alpha is not A conjugate. Why? Because if alpha were A conjugate, I could easily reinstate this A without losing balance. And similarly, I could reinstate conjugate A here without losing balance. So alpha cannot be A conjugate. And for the similar reasoning, beta cannot be A. Another thing we can assume is that this brace is at minimal length, meaning that I cannot move this end left. I mean, in general, I could have several possible decompositions. I take the one which has this bit shortest. This gives me another easy way of eliminating cases. So alpha then cannot be B, because if it were B, I could move this bit one step left, and this limit one bit step left. I would add one B to capital B and remove one B from capital A and still keep the balance. So this means that A wouldn't have minimal length. And similarly, beta is different from conjugate B. So I only left with two cases. Alpha must be either A or B. I do the case alpha equal A. The case alpha equal B is similar. So if I say alpha equal A, then beta must be B. Because we know already that we eliminated a lot of cases. And if beta were conjugate A, then I would have a trivial decomposition here. I would have A conjugate A, which is easy to see that is not possible. So this means that basically beta equal B, and then we can move by one step the end of A to the right and the end of B to the right. So we moved one B here, and we removed one B from capital B. So basically we move one step both limits of the brackets. And again, we have A and B underlying a balance string. Okay, how many times can we repeat this sliding argument? Well, we can keep doing this until, as long as we see B on the right of this limit and B on the right of this other limit. But at some point we must end. Okay, we end either when the length of this brace B is 0, which is a corner case in some sense, or otherwise, at some point, B, by moving to the right, will meet conjugate A. The other cases are trivial. And this, the right hand of A hasn't met the cancelled letter yet. If we meet the cancelled letter, then it's easy. We just reinstate the two cancelled pair, the cancelled pair, and we have a decomposition. So the only case is that the only possible case we cannot really resolve is when we meet by moving to the right conjugate A. However, if we meet a conjugate A by moving the end of B, this means we have found a bump. And if we have found a bump, but A hasn't still touched the cancelled A, it means we have found a bump which is shorter than the one we removed. That's why I picked the minimum one. So this allows us basically to prove that we can go from a bigger pair of strings to a smaller one by removing bumps one at a time, as long as we pick minimal bumps. This is basically the key argument. Okay, I will try to speed up. So lemma 2 is basically the ugly version of the sliding argument that we just saw. Yes. And it's ugly, but the proof is manageable. It's just combinatorial. And then by uniting this lemma to the previous one, we easily obtain theorem 1, which is about balanced decomposition. So it just says that we can always unbalance the composition. And I just end with what I have in Isabel. Not much, to be honest, but yeah, I have some stuff here. So I have a definition about the composition. I have some silly way of associating letters and conjugates to integers, because I will need that. So notice that conjugate A is just rendered in Isabel as capital A, and similarly for the other letters, because I couldn't bother to put the overlay line. And so I have this style mapping between letters and integers, because that's one way I found to move to implementing the proof. And then this other bit is more computational, so I have some computable definitions to check the balancedness of stuff, and also the validity of the composition. So the valid is valid, it's just a predicate checking whether the composition is balanced and it has not more cuts than allowed, and so on. And then I have some very trivial lemma still, which is not very exciting, to be honest. But it's just about checking when you have some string which is balanced, and what does it say? That it means just say that if you have a letter, then you also must have the conjugate and stuff like this. So really quite trivial stuff. And this is even more computational, so it's not used for the proof, but just to do experiments here. So I have a way basically of computing all the possible decompositions and all the possible strings of a given length. And this was somehow useful, as you see in the last slide, because I can compute stuff like this. I can compute all the decompositions of a given string, and I can use that to generate all the decompositions. And yeah, this was useful because by doing by generating all the possible strings and checking the decomposition, I found this, which I don't know which is true or not, but basically, if you have some particular tuple of factors which is balanced, and you compute all the decompositions, and you see that all the decompositions split one of the strings all in the same position, then in that position, the two characters before and after must be identical, which I don't know if it's true or not, but seems to be hold for very, very many cases. And one thing which really bothers me is this. So as you remember the sliding arguments, we saw this case, but you could also have this case. The argument is basically the same. We keep sliding and use minimality of the bump. But I don't know how to avoid repeating the proof, because in this case, you are inside one factor, and in this other case, you are inside two different factors. So this bothers me. I cannot find a way of avoiding repetitions in the proof. If anybody has some idea, I'd be glad to hear about that. Yeah, that's it. And just the references to finish. Thank you.